Recording in progress.
Hello, everybody. Welcome back to our conversation about chemical equilibrium. We just learned last week how we can determine the concentrations of different substances at equilibrium by utilizing the equilibrium constant and the method of keeping track of changes from initial to equilibrium state that we call ice tables. So we're going to be doing a little bit more equilibrium stoichiometry in this portion of our lecture series. However, we are going to be classic chemists in the sense that we are going to try to find ways to cut out a bit of that quadratic formula, algebraic kind of work that we have to do when we do our ice tables. So let's jump in and talk about when we can maybe do some approximations and make life just a little bit easier for ourselves. So when we talk equilibrium, there is this approximation that can be made that's called the small x approximation. So let's talk about scenarios under which the small x approximation is valid, what it even means, when we can apply it, things like that. So in scenarios where we've got the small x approximation, we are looking at reactions with K constants that are either very large or very small. So if we are a very large equilibrium constant, this means that K is significantly greater than 1. In fact, I'm going to go ahead and say if K is greater than or equal to something on the order of magnitude of 10 to the 10 to the positive 5, then we can call that large. So let's set that as our limit. And when K is very large, this means that we are an incredibly products-driven reaction. Meaning in our equilibrium mixture, we would expect to have higher concentrations of products than we do of our initial reactants because the K is so large. So remember, K is a proportion of concentration product raised to their coefficient over concentration reactant raised to their coefficient. So if K is a big number, then either this numerator has to be large or this denominator has to be small. That is only true when we have at equilibrium a large amount of product and not a lot of reactant present. Okay, what about the inverse? What about scenarios where K is very small? So K has to be significantly less than 1. And let's set a similar bound for what we're calling very small, enough for us to use this approximation. So this would be something like Ks that are less than or equal to the order of magnitude of 10 to the negative 5. And if we are looking at such small equilibrium constants, then this means that we are a reactants driven reaction at equilibrium. So again, if this is a fractional number, that can only be true if the numerator is small and the denominator is larger than that. So that means we have to have in our equilibrium mixture more reactant present than we do product. That is what it means to have a K that is very small. Now, in both of these scenarios, the K values are so large or small that we can assume the change from initial to equilibrium state is negligible. In other words, X for some species, not for everything, can be approximated as 0. That's what it means to have a negligible change from initial to equilibrium state. So this is what we call the small x approximation. And the idea is that for some species, in our ice tables, x is going to be approximated to be equal to 0 because we know that there's an overwhelming amount of either product or reactant present, depending on our K value, and that the change from that overwhelming amount initially to the equilibrium amount is going to be like relatively very small. So this is what we call the small x approximation. Let's practice it. So here we have a dissociation equilibrium for hydrocyanic acid. So this is HCN that is in solution and dissociating into H plus and CN minus. And while I like things to be centered, let's move this over because we know that we are going to be doing some kind of equilibrium calculation, namely because I'm asked what are the equilibrium concentrations of each ion. So I want to figure out my goal, which is to figure out concentration H plus at equilibrium and concentration cyanide at equilibrium. That's what we want. So since we want our equilibrium concentrations, and we know that the solution was prepared to have an initial molarity of 0.15 molar, we have the capacity to build an ice table here. So I know this language maybe at the end here, it might be a little confusing. So we've got the problem, dissociation equilibrium for hydrocyanic acid has an equilibrium constant of 4.9 times 10 to the negative 10. So right off the bat, we see that this is kind of like perking our ears up a little bit to maybe allow us to do small x approximation, just because this is an incredibly tiny equilibrium constant. So this is a very undissociation or reactants favored equilibrium. And it says, what are the equilibrium concentrations of each ion in a 0.15 molar hydrocyanic solution at equilibrium? So I know it says at equilibrium here, but we have to remind ourselves about how this hydrocyanic solution was prepared. Like how would you go into the lab and prepare a solution? You would go and measure out some amount of solutes. We would measure out either a solid or some pure liquid. And then using the molar mass and the mass of that solute added, we would convert to moles and then divide that by the total volume that we dissolved that solute in. So when it says 0.15 molar hydrocyanic solution, this is talking about like at the moment of preparation, like the math that we've done, the work that we've done in the lab to prepare the solution is so that we've got this kind of initial concentration of 0.15 molar. Because when we do our like molarity calculations in the lab when we're preparing solutions, we don't start at equilibrium, right? We don't think about what would our concentration be at equilibrium. We say, let's just make the solution and then understand it goes to some equilibrium state. So all that is to say, this is what I know about my initial system, right? I've got my amount of my hydrocyanic solution initially. So this is 0.15 molar initially. And since this is such a teeny tiny 10 to the negative 10 equilibrium constant, we know that initially especially in this reaction or this dissociation, there's going to be no presence of either the acidic H plus or the cyanide ion. So we can say that their initial quantities are 0 molar. And I'm just keeping my sig figs here, 2 sig figs as given by my original molarity. All right, let's continue on as if we were doing just a normal ice table and kind of preparing ourselves for the quadratic formula, and then bring this small x approximation into play. So everything is 1-to-1 here, which means that the hydrocyanic acid is going to decrease by some amount x, which results in some proportional increase in the amounts x of H plus and Cn minus ion in solution. Meaning at equilibrium, I'm going to have some concentration of hydrocyanic acid of 0.15 molar minus x molar. And then I'm going to have x molar non-zero concentrations of each of my ion after the dissociation occurs. So let's ask ourselves a question. Where can we assume that the change in concentration is small enough to approximate as 0? So we've got 3 options here, right? We've got the change in the hydrocyanic acid in solution, the change in H plus, or the change in Cn minus. So the question is, which of these changes is going to be relatively small given what we know about Ka, or excuse me, Kc? So I'm going to put Kc here. This was again 4.9 times 10 to the negative 10. Very, very, very small Kc means that we are favoring at equilibrium the undissociated form of hydrocyanic acid. So if we consider like what quantity is going to have some negligible change, then it must be the amount of hydrocyanic acid, because we know that overwhelmingly in solution, because this Ka is so small, there's going to be a huge amount of hydrocyanic solution, hydrocyanic acid in solution. And then when it shifts to equilibrium, like that general change to equilibrium is going to be pretty, pretty small. We cannot say that the amount of each ion made at equilibrium is 0, because that's not how equilibrium works, right? At equilibrium, we have to have both reactants and products together in an equilibrium mixture because we have a rate of forward equal to the rate of the reverse reaction. But it could be really small enough, in fact, to say that this more or less stays the same, and then this is teeny tiny. So we're going to say that this is equal to 0 here. So we're going to make the small x approximation, which it says basically the concentration of each CN initially is more or less equal to the concentration of each CN at equilibrium. So how does that impact our equilibrium calculations? So if I were to build an expression for my K constant for this reaction, this dissociation, I would have to do my products. So these are my ions, concentration H plus times concentration Cn minus, over my reactant, that is concentration HCN. And these are all, again, at equilibrium. So I'm going to drop this little subscript EQ. And instead of doing a string of equivalences, let's kind of move our work up here. So this means subbing in what we get for our ice table. We've got our K, which was 4.9 times 10 to the negative 10, being equal to, in the numerator, that is x times x, or x squared. And in the denominator, that is our 0.15 molar minus our x that we are approximating to be 0. So this is our 0.15 molar. So now I need to solve for x. So I've got x squared is equal to 4.9 times 10 to the negative 10 times 0.15 molar. Okay, let's see here. Do I have this number? I might not. I don't. But that's okay. You guys have calculators. So once we want to solve for x, we would then take the square root. So notice no need to use the quadratic formula here. And when I do this, I get a root of 8.6 times 10 to the negative 6, which means that my concentration of H plus at equilibrium, which is equivalent, right, to my concentration Cn minus at equilibrium, is equal to the value of x, or 8.6 times 10 to the negative 6 molar. So we have answered this problem. We have found the equilibrium concentrations of our ions without the hassle of using the quadratic formula. Now let's verify to ourselves that this was an appropriate assumption to make, right? Like this approximation worked for this reaction, meaning let's do the full-on quadratic equation answer to this question. So I'm going to grab my calculator just so we can get the actual values for our quadratic formula. So again, we had HCN aqueous in equilibrium with its H plus ion and its Cn minus ion. If we are building an ice table, then we know we've got 0.15 molar, 0 molar, and 0 molar initially for each of our three substances. Then the amount of HSCN changes, it decreases by some amount X, resulting in a proportional increase amount X in each of our ion concentrations. So at equilibrium, this becomes 0.15 molar minus X, and then X again for our ions. So if I'm setting up now our kind of standard ice table, this would be x squared, the numerator, and 0.15 minus x in the denominator. Another way to do this is to multiply over. So I'm going to have 4.9 times 10 to the negative 10 times 0.15 minus x is equal to x squared. So 4.9 times 10 to the negative 10 times 0.15. Doing our distributive property here, this gives me 7.35 times 10 to the negative 11 minus 4.9 times 10 to the negative 10 x is equal to x squared. And then rearranging so that we do have our quadratic formula structure of 0 is equal to ax squared plus bx plus c. We find that we have 0 is equal to x squared plus 4.9 times 10 to the negative 10x minus 7.35 times 10 to the negative 11. And now we have to do our quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is equal to, our b here is 4.9 times 10 to the negative 10. Negative b. Let's try the positive root first. Square root of 4.9 times 10 to the negative 10 squared. Let's see here, minus 4 times a, which is 1, times c, which is negative 7.35, times 10 to the negative 11, all over 2 times a. Okay, so let's see here. I'm going to tackle my root first. And let's keep it plus or minus. Let's see what we get in our root. So 4.9 times 10 to the negative 10 squared. Okay, and then we subtract out our 4 times 7.35 times 10 to the negative 11. Okay, and then we take the square root of that. I have a sign issue here. This has to be a plus. So there we go. 4.9 second e negative 10 squared plus 4 times 7.35 second e negative 11 square root. Okay, so I've taken care of my square root here. That is 1.71 46 times 10 to the negative 5. Okay, we are definitely going to want to pick our positive root. That is the only way that we are going to get a non-negative number. And this is all over 2. So this is then 1.7146 times 10 to the negative 5 minus 4.9 second e negative 10. And then divide by 2. This gives us 8.57296 times 10 to the negative 6. That was our value for x, which is also equal to our ion concentration. And we see that this number is really similar to what we got earlier, right? 8.6 times 10 to the negative 6. But just saying that something is really similar is not enough. So anytime you have to validate or justify or like prove to yourself like, okay, like I'm doing all right with the small x approximation, it was appropriate to use here, you need to do the 5% error check, meaning do my values when I use the approximation or not agree within 5%. Now, this is why I selected for you such insanely large and small, meaning 10 to the plus or minus 5 values for you to say that when this is okay to do your approximation, just because those are values that like are incredibly large or incredibly small to the point where like x is almost always going to be approximatable. There's a word for you, as 0. But let's go ahead and do our 5% error rules. So we are going to do a percent error. So this is going to be the absolute value of the difference between what it should have been if we were not applying our approximation minus what we got, which was 8.6, right? Yep. over what it should have been, meaning if we had not cut corners, and then to make it a percent times 100. All right, let's see what this is. So minus 8.6 times 10 to the negative 6. Make that positive, and then divide by 8.572969, just keeping all my digits to avoid a rounding error, times 10 to the negative 6 times 100. Yeah, this percent error is 0.315%, which is definitely less than 5%. So it was absolutely valid because our percent error was less than 5%. We're good to go. So in this case, like in this example where we're looking at this dissociation of hydrocyanic acid, this was looking at a K that was incredibly teeny tiny small, right? 10 to the negative 10. However, as mentioned, there are approximations that can be made when K is very large. So in our next video series, we're going to talk about what happens if K is incredibly large, meaning we are a very product-driven reaction at equilibrium. And what does that mean about what approximations we can make, how the system looks, how we treat what's going on in the chemical reaction, and so on. So I'll see you in our next video where we continue our conversation about equilibrium stoichiometry using the small x approximation for equilibrium reactions that have very, very large Ks.